And you gotta stop meetings.
Okay.
Sure. Yeah.
Where are we going? You work?
Yeah.
Not good?
You know what? That would actually.
How can I make it work? Wait.
Sounds fine, I can feel seasonal depression.
Yeah.
Leaving.
Yeah. We're about to jump forward. March 8th or 9th or something.
The losing. Or.
Yeah. The sun sets at a later time. Which is nicer. Because then you go out of class and not dark.
Yes.
Okay. So we're talking today about constitutive relationships. And in particular, we're going to be looking at the relationship between how velocity is transferred in the fluid. And we're tying this back to the idea of forces. Okay. The homework, I just posted it this morning. It's from chapter 4. It will feel like a lot. I'll try and get these back to you today. I'll grade them in between this class and the next one. I really recommend that you're working together. I haven't had a lot of folks come to office hours. The idea with the homework is not to get it right, right? So the goal here is not to find the solutions online and then just copy them. It's not to like listen to your friend who did it right and just write what they wrote. It's for you to struggle with the material such that you feel like you're interpreting it properly, right? Because if the homework is like working out, right? And the class is like prepping you for that process. And at the very end, you want to be strong, not have taken steroids. Right? Okay. The homeworks, they don't really get like more complicated. They add more concepts in. There's no final project for this class. But I will expect you to have a really innate sense of the mathematics. My goal for you is to walk away with a deep conceptual understanding of the math. And then on top of that, I'll expect you to know how to do some of the mathematics itself, right? For me, that's a secondary goal. Maybe for you, that's a different goal. We'll talk about your goals. We'll talk about your progress in the class and our first check-ins, which are next week. So I will expect you today through Friday to contact me for your 15-minute to 30-minute appointment. And then we'll talk about your progress in the class. I'll give you all your homework. Okay? Okay. Let's go. All right. What is a constitutive relationship? Hell is that first word, right? Constitutive. What does that kind of look like? Yeah, that's the definition. But what is the word itself? Constitutive.
And concern.
The con, right? That's what you're drawing your eye to. What about the constitutive? If I do that, what does that look like? Constitute. Yeah, this constitutive comes from the word constitute, of or how something is made. The constitutive relationship describes the relationship between the material properties of the fluid. How is the thing constructed? And in this particular circumstance, we are using it to describe something called the stress tensor, which is the relationship between how forces create velocities. And that is a material property, right? So unlike when we talk about, say, if I just throw you a ball, or if I throw you a banana, doesn't matter what the ball or the banana is made of, right? That's not the case for fluids, because there's a relationship between the material properties itself and how the velocity is transferred because of the force. Does that make sense? So you see how it's different? You can also think of this as a constitution, right? Constitutive of or making up constitution. Okay. Okay. So we were writing something. We said T is the symmetric tensor, stress tensor. I don't want to draw here. Is that the idea? Were you originally? I want to draw here. Okay, so let's start here. T Ij equals. What's that?
Is it the negative?
Yes, yeah, that's the next line. The line right before that is TJI. So just this part here says that it's symmetric. Good, and then your point was that Tij is what? Yeah, Kronecker delta Ij. Okay, and just to make sure that we're all on the same page here, we're using tensor notation because this is a tensor. So let's just make sure that we understand the tensor notation. So here on one side, there are no repeated indices. If there are repeated indices, what am I doing? Let's say this is A, I. What is that equal to?
That was gonna be like one.
Not quite. So this requires, we can write it in two different ways. We're gonna, if there's a repeated index, we're gonna sum over that repeated index. So I can either have the value of 1, 1, 2, 2, or 3, 3. Right? Because I needs to be equal to what would normally be J, but in this case, it's both I. Or if you're thinking of it in the context of spatial dimensions, this is fine. That's how we write tensors. When we're only writing one of them and there's not repeated indices, that's telling you that I'm only talking about a single component. Because if, for example, I have this in my equation, i's and j's repeated, whether they're i's, whether they're j's, whether they're k's, you have to sum over those in order to get the result. So I might only write one term, but I might be hiding the fact that there are 3 terms. Does that make sense? So this is the tensor summation rule. And we'll see this in more practice at the end. Okay. So we were writing Tij, so this leads to Tij, and how does it look on the diagonals? What's that?
The negative p.
Exactly. So just negative p, negative p, negative p. Good. And do we know anything about the off diagonals? They're symmetric, right? So this piece here must be this piece. This one has to be this one, and this one has to be this one. Okay. So, we are actually going to use, let's see if I say this in the next one. Yeah. We are going to basically separate this stress tensor. We're going to separate pressures from fluid motion. Okay, so right now we've just talked about pressure. The source of pressure is due to the fact that you're in a fluid and you may have more stuff pushing on one side than the other. But this could be completely static, right? In fact, fluid statics have pressures without velocity. Okay. All right. So let's add in some velocity. Make sure that we're nice and confused. We're going to use the letter tau. Okay. So we are going to write that T, that's chalk is getting disturbed. Tij is minus P delta ij plus tau. Essentially, we're just kicking the can down the road. So all we're doing is we're saying, okay, now we have to define this thing called tau ij. What is it? Okay. So the name of this thing, you don't have to memorize this, but you can call it the for stress. Media charge stress. Okay. And let's see, how much do I want to show you of this? You can find the derivation in the book. I think it's better because there's a lot of summing. Well, let me show you how bad it looks, and then I'll show you the answer. Okay, so this piece here, tau ij, is equal to A I J M N S M N. Okay. Now I haven't defined what K or S are, but what we're doing here is we're thinking about that tensor index rule, right? So you can have a look at that and you say, okay, so this on the left-hand side is talking about a single term, because I and J are not repeated. And so if I look on the right-hand side, the indices must match. So left, I have IJ. So the right, I need to have IJ at the end of the day. So if, for example, I have a repeated index here, I can imagine that it'll disappear because I'm going to sum over it. And similarly, I have another one, N. See it twice, it's going to disappear. So the only ones that are going to be left over are IJ. So I'm like, oh, that's great. No worries. Okay. Now let me show you a way to do it wrong. Okay. If I do something like this, okay, that's a no-no. Why is that?
You have two of the same. It's supposed to be one like term. You have two same. indexes.
I have the index I 3 times. Right? So I'm confusing myself because I don't know which of the places I'm summing over. Right? This is 4 indices in order to tell you where you are. Right? This is the 1, 2, 3, and 4 position. Am I summing this guy over the 1 position or the 4 position? Or am I just summing these two over the 1 and 4 position, and I don't know what I'm doing over here, right? So in fact, we want to use different letters here so that we never have 3 or more of the repeated index. The most you can have the index show up is twice. Okay? And similarly, if I had another term, like if I was over here going S, I, J, I'd be like, oh, that's still okay, right? Because each one of these is matched up with each one of these. If I did this, is that okay? Why not?
There's the first and second one, the same term or indexes.
This one here
In terms of like.
and this one here. Yeah, so this one would be really confusing, right? Because what I'm doing is I'm adding here, I, J, these repeated indices need to be repeated here. That's what I'm summing over. And now I don't know what I'm doing with these. Right? So you find them in pairs. Is that okay? Yeah, we'll see this in practice. Okay, so let's think about this for a second. How big is this tensor?
That's the term,
What?
just a single term.
Yeah. But how big is the tensor that it comes? You don't know the name of the tensor, and we don't really care about that. Yeah, it looks fourth order, right? There's 4 different indices there. So if I thought of them as X, Y, Z, right? How many different terms do I get? A vector has how many terms? A vector in 3-dimensional space? 3, X, Y, Z. A matrix, a 3x3 array has 9. Okay, a 3x3 array has 7. A 3x3 array has 81. So this tensor, the place that it calls home, has 81 different components that describe it. Right? This is why tensors are beautiful. Because instead of writing 81 terms, I just have to write that. Yeah, and you can go and of course you can look at all of the different things. We can calculate them individually. And then later on, when you get better, you can use a computer. Right? Okay. I could write this out. Do you want to see what it looks like? Maybe just for edification, we'll show you just an example. You don't need to memorize this. This is what the KIJM tensor looks like. IJM. It's silly. It's lambda, a constant, times delta IJ, delta MN, plus mu delta IJ, sorry, this one, IM delta IN, plus gamma delta IN delta JM. Did I do this right? It's J. Very good. Nice catch. Right? Now this is a very silly one. Why is it silly? They are doing what I talked about before. Look, IJ here, IJ here, IJ here, IJ here. right? And then here, and then here, and then here, and then here. Before I talked about the fact if I'm missing, if I don't have MN, they must disappear by some. Here there are all four indices. This is like the address that you would send mail to. And this is the location. Each term has the location of where it's located. I, J, M, N. You see? So why is this one silly? It's not that.
They're all independent, right?
What do you mean
In
by-
terms of the coordinate system, or
Not exactly. What does this do? What does delta I, J do? Yeah, it is equals 0 when they're not the same. So it's only non-zero when they're the same. So it basically selects one index and makes it the other. Right? So let's see if we can understand this. For if I use here I, J, M, N, okay, let's do 1, 1, 1, 1. What do I get? First term? Oh, okay. 1, 1 is 1. 1, 1 is 1 times 1 is, so I get lambda. So this is lambda times plus u plus. Yeah, good. Okay. Okay, now let's change this back one. So 1, 1, 1, 2. This first one,
one,
1. Second one,
zero.
0. So that's gone. This one,
One.
1. Good. This one, I hear different answers. 2, 0, 1. Okay, so here J is 1 and N is 2. 0. So this term is 0. This one? And it's also 0 for that same reason right here, right? Okay, so when this one is 2, it's not 0. Or it's 0. Okay, what about I is 1, J is 2, M is 1, and N is 2? Does that make sense?
Mhm.
I and J is 0. So this one's gone. I and M. 1. 1. Yeah, this one's 1. 1. Oh, so we have this term. What about this last term? Do you see the structure of this array? As you go through the 81 terms, you basically are just walking through and seeing if all the rules apply. And then you find the answer, you plug that into that location. If you had a computer, right, that'd be really nice because then you could write 81 terms instead of having a giant sheet of paper with mostly zeros and then in other cases, individual ones, right? We feel okay about that? Okay. This is properties of the fluid. We're not going to talk about how we derive them, but they're essentially, they depend on the thermodynamic properties of the fluid. Tij here, right, is a symmetric tensor. How do we know that? Oh, sorry, tau ij is a symmetric tensor. No, we don't need anything about its properties. We know that it's a symmetric stress, but we know that it's symmetric because of something else. We know that this one is symmetric because this one is symmetric. Tij is symmetric, right? And this is what makes it, right? So this thing here happens only on the diagonal. The Kronecker delta only affects the diagonal. So therefore, the off-diagonal terms are provided only by this thing. So if this thing here, Tij, is symmetric, then tau ij by definition must be, right? Okay, so we can clean a lot of this up. We can use some requirements here about the fact that there's symmetry. And we can just write out let's write this one out. We're gonna write that tau ij, people see this okay? Is equal to 2 mu Sij plus delta, or sorry, lambda S M delta. That look weird? That seems silly. We haven't defined what SMN is yet, but let's see if we could derive that from here, right? So you have the IJs, those are not going anywhere here. And we're repeating the indices M and N, right? So this first term, the IJs matching, right? So IJ, gives us 2 mutes. Here's the mute. We sum them. So when they go through the sum, you get 2 of these. And here, you get 1 of these multiplied by SMN only if I and J are the same. Otherwise, it disappears. I haven't described your S's yet, so don't be worried.
SMM.
M, yeah. So this is the repeated index here. And just like we said before, here's the location, here's the address of this term, the IJ location, IJ location, IJ location. You feeling more comfortable with tensor notation? Yes. All right, whatever, we'll deal with it. Yeah,
So for that equation, what you're doing, are you substituting the 4.29 equation with 4.28? Or the,
yeah, we're taking this thing, right? We're using it here. Yeah. We're taking this one here, putting it here. And then we're writing out the terms and we're using the fact that it's symmetric. Because tau ij equals tau ji. Right? And that's really important because that's what gives us our factor of 2 here. Right? Okay. So what is S? Well, S is really interesting. SMM is del dot U. What does that thing mean? Yeah, this is the divergence of the velocity. We said something earlier on that if this thing equals 0, then that means something. You remember that part?
The velocity in all the directions is 0.
That is one way to do it, but that's the boring one. We said fluids that have this thing equal to 0 have a special property. And we called it incompressible. So now to go back to the definition of this, which is that this is the volumetric strain. What does volumetric mean? It means happening on the volume, right? Compression and expansion, as opposed to any type of shear. So we are breaking apart different terms here. This one here is the compression term. Does that make sense? So let's have a look. Let's go back to the beginning. I have contributions from pressure. Then I have two terms, okay? This one here is compression. Different from pressure. Note that, right? And what is this one? I mean, this is the stress tensor, so yeah. But let's be a little bit more specific. What kind of stress? There's stresses and strains. We want to be specific about what, like I said here, that we're squishing the box. Let's use our hands to describe this tensor. This is the shear. And if you look at it carefully, it will make sense. This is S-I-J. When I acts on J. Okay, and we're going to see it written out in a few seconds. But essentially what we're looking at here is this is a term for shearing. Okay, like force in X on Y. This one here, compression, expansion, rarefaction, pressure. Okay. Okay, so let's put this all together. T(ij) is minus P delta ij plus this thing here, 2 mu Sij plus lambda, I keep saying delta, I'm sorry. S M M delta I J. So let's see if we can use this idea, this concept. Let's take an incompressible fluid. Is it possible to deform an incompressible fluid? To deform it, to change the. This is a good fight. Why don't you talk to your friend for 5 seconds? We'll see what we'll come up with.
I would
I think it's a direction.
say yes, because the incompressible fluid is only delta U, and then you still have the other two terms.
Yeah, if the fluid is incompressible, can I deform it?
And so
If
we,
it's gonna.
Well, if it's gonna compress it, to volume.
It's not a very- You can't compress the books without shoving.
But then he said like, yeah, compression and pressure, same thing.
Did you get that?
I think we know that. It was.
But here's the piece.
Yeah. They have one of those.
Oh, right.
I got it.
Split it. Be nice. Yeah, it's hard as a rock.
That boy is not compressible.
You're gonna need to dunk that in milk. Okay, so what do you think?
Yes, you can still change.
Yes, you can still change it? Are you convinced of that by the math, or do you just have like a vibe?
Both.
Both. Okay, tell me about the vibe first.
Tell you the what?
Tell me why the vibes say that that's true before we go into the math.
Because you don't only need to press it.
Right, you don't only need to compress something to change shape. Can you give me an example?
Water. Not compressing it, but you hold it.
Very good. Right, for the most part, the world that we live in, water is incompressible. And yet we change the shape dramatically, often with forces. Okay. What does the math support that statement?
we said, if del dot U is 0, then it's incompressible,
Mhm.
we still have two other terms.
Good, yeah, that's exactly the way to think about it, right? So you see something like SMM, and you think to yourself, oh, that's del dot U. And I think to myself, del dot U, well, that means, is this thing compressible or not? Because the only thing that's gonna happen here is it's either gonna be 0 or it's not. Right? I don't really care what the value is. It either exists or it doesn't. If it exists, then this term is real. It exists, not real, you know what I mean? If it doesn't, then this term disappears. Cool. All right.
I have a question. Is the second term? It not in 2 mu Sij?
Yeah.
Is that how resistant it is to being like to shearing? Is that what that's
We have not yet defined Sij.
Oh.
Once you see the functional form of Sij, we'll have a better intuition for what it means. We are associating it with the vibes of shearing right now. Okay.
Okay.
So we start with just like hand waving arguments because we really want to think about how did we come up with these arguments. We had water, we had different fluids in a lab, and we were trying to understand how they distributed force, right? And so they looked at certain things. They looked at pressures applied to them. They looked at whether or not they could compress the fluid and how that creates change, right? This is not true for every single fluid because not every fluid behaves this long. We are talking right now about a special class of fluids called Newtonian fluids. We haven't described what that is. You're going to see it very shortly. The Newtonian fluids are only valid when they apply forces in the way that we're about to describe it. So if you've ever heard about something like oobleck, which is basically cornstarch and water, I think, in equal parts or one more than the other. What it does is as you hit it, it actually gets harder. So if you put your hand on it and you just leave it there, it will sink in like a fluid. But if you smack it, it'll hurt. Now, of course, if you jump off a bridge into water, that's also gonna hurt, right? Because concrete and water at very high speeds act very similarly. But generally speaking, if you jump into a pool of water, you're gonna be fine. If you jump into a pool of oobleck, it's gonna hurt, okay? Because it'll first get hard and then you'll sink in, right?
Can you
And-
pull your hand out of oobleck fast?
I don't know, that's a very good question. Right, and this has a little bit more to do with how are the forces, so you're saying pull it out as opposed to push it in.
Yeah.
So how do the forces transfer velocity? Right? Do they dissipate it easily or do they do something else? And what we're going to see here is this really is a description of how velocity is coming from surface forces. So there's going to be a relationship on one side between the velocity and something. Okay. I think I said everything I wanted to say here. Let's delete this and then. Okay, I just said that. At the top here, so you will find in the book that equation 4.35 talks about how incompressible fluids don't expand or contract. Okay, that's the definition of incompressibility, right? So maybe we haven't said anything stupid there. We can define a few of these other things. So you can find the pressure term and you can find the deviation from the pressure by looking at this piece here, right? P, and you can rewrite it in terms of the tensor. So you can take this term here and this term here, you put them on the other side, and you define what the pressure is as a function of all these other relationships. And then you can take what's essentially small deviation. So what you do is you say, okay, here's P, and I subtract from it just P prime or P little bar. This is something called perturbation theory. What we do when we do perturbation theory is you look for small deviations away from the mean. We say, how do they change? Are they linear with some property? So for example, if I change the velocity by a little bit, do I get a big change in the pressure? Right? So on and so forth. So I'm not going to work through that there, but the result essentially is that you just lose this term if it's incompressible. Okay. And I'm now going to define some cool stuff for you. Here, you've been wanting to know what that is. You're curious what that was, right? Biggest mystery of the day. Okay. So we can define something called, just put it here. Everyone can see this okay? Okay. So this is mu nu, which is going to be equal to lambda plus 2/3 mu. Okay. This is called the coefficient of bulk viscosity. Okay. These are material properties. Let's see, what else do I want to say here? We're generally going to wrap stuff up into this to try and make this easier. You'll see this definition, the word viscosity, the word bulk viscosity, of course, meaning that this is the viscosity of the fluid as a whole. And when we think about how to communicate generalized stresses by the fluid, we have to think of them each with their material properties. So if you want to do some calculation for the entire Earth, and you have, say, the whole ocean that you want to consider, this property, which is a thermodynamic property, may change with depth because temperature is changing, because the pressures are changing, right? So the viscosity of the fluid can change. So even though that's a constant in our equations, solving them in practice can be quite tricky. So when we write that, we can write this generalized stress tensor equation. It looks worse, but it's fine. It's Tij, which is minus P delta Ij. What's this term? What's this first term called? The pressure term, very good. So did I do this all just to fuck with you? Well, I defined some new thing called the bulk viscosity. And then I found the pieces here, the lambda and the mu, and I rearranged this equation such that now we repeat this weird quantity, SMM, SMM, and here I have mu and I have mu naught. So this is the very generalizable equation, the stress tensor. The 9x9, or sorry, it's a 3x3, so nine components. It's actually not horrible. You know, here you have a pressure term, it's on the diagonals, moderated by something. I don't quite understand what that is. But this one looks reasonable. What do we call that? Yeah, compressibility, right? So the compressibility term is still there. Oh, and in fact, it's right there as well. Okay, so it's the same thing that we saw before. We just rearranged it in terms of this thing, right? Thing that we actually measured with fluid. Makes sense.
I thought, in the book, it says that mu v is 0, right, and that's when you substitute it into the big equation right here. Oh, my. Okay, I'm trying to put them together.
Yeah, so using the Stokes assumption. So now the question is, what's the Stokes assumption?
It's 0.
So this is the Stokes assumption. Now look at how that's written. Is that the Stokes law? Is that the Stokes theorem? No, what is that? That's an assumption. When have you ever had a physics class? They're like, okay, we're gonna work off the idea that this assumption is correct. Because fluids are fucking hard. And you gotta assume some stuff to get started. Okay? So you're right. That thing up there, that thing that we defined, is a Stokes assumption, that's 0. So what happens to that third term? In practice, it's not used. Okay.
So that two, you said that's like the moderator, what is that?
Fair.
Right after pressure.
Yeah, so this one before, so we said 2 mu Sij, that was like a shearing term, and this is like a compression term. But the thing is, I never told you what this thing is, the lambda or the mu, right? So this is like a viscosity. And I didn't tell you anything about this. This is like a pressure, right? So these are material properties that depend on the fluid's thermodynamic state. And the reason why we want to add this over here is because this thing plus this thing tends to equal 0 in fluids. So then we can use that idea here, the Stokes assumption, to get rid of this term. You mad? And if I said something wrong, that's totally okay, right? There's a lot of letters here. So if I've confused you somehow, just raise your hand and be like, just contradicted yourself. I'll make sure that I'm saying it properly. Yeah.
Going from this bottom one to the middle one,
Yeah.
are you substituting that top equation for lambda?
Yeah, so this thing here, yeah. Yeah, so essentially what we want to do is we want to get rid of this. So we write it in terms of mu nu, which is then gives you this. And that's why you put this minus here. Yeah, the 1/3. Well, it's 2/3, right? The 2 comes out, but the 2 already exists here for us.
That's what it is.
Yeah, the only thing to think about here is now we have this fully in terms of this quantity that we actually know, the viscosity. As opposed to this thing, which you're not familiar with. Okay. Yeah. So this is an okay assumption if the bulk viscosity is small. Notice that it's not 0. I just said small. Okay. All right. So now let's finally talk. Yeah. Okay, so what does it mean for something to be Newtonian? What was Newton famous for? Being that guy? Incorrect. That is not what he's written on his tombstone. He is him. What did Newton develop or help to develop? The calculus, right? And the calculus was determining rates of change, right? And he worked with other mathematicians, probably took credit for some stuff that he shouldn't have, whatever, okay? We still think of the Newtonian fluid as the one which represents the relationship between the forces and the stresses, or sorry, the stresses and the velocity linear. The major difference here is simply whether or not the fluid is linear. Okay, so what do I mean by that? Okay, let's see if I can write it. Tau 1, 2 is equal to another fucking constant. Okay, so what am I saying?
In the velocity of one dimension, respect to the position in another.
Yeah, so that is reading it for sure. What am I saying as far as like, how would I conceptually tackle this beast? That's the requirement for Newtonian, that's correct, but the derivative on the right-hand side. So the top part says the rate of change of velocity with respect to some position. Right, and I, J are different there. So let's use the example, let's maybe say UX versus Y, right? So how is the velocity in X changing in Y? Let me show you an example of that. Okay, okay, here is fluid. Here's X. Here's Y. Okay. Up here in the fluid, it's moving fast. Okay. If I pull the top of the fluid, perhaps, I'm not talking about how I create it right now, just imagine that I'm moving it. And what does it do? It pulls all the layers below. Now, does it do it perfectly? No, there's some loss. That's captured in that constant. Some fluids are going to be really good at it, some fluids are not. How strongly is the velocity communicated, for lack of a better word, in the fluid? Make sense? But how is the UX velocity changing Y? And that is the source of strains. Okay. Okay. We talk about a Newtonian fluid, not sorry, non-Newtonian fluid by making this generalizable. So we can say something like tau 1, 2 is m gamma dot n minus 1 bu1. Shoot. So, in a Newtonian fluid, n is 1. So what happens to the exponent for gamma dot? It's 0. And so therefore you get a 1 there, right? And what is m? Well, m is just the fluid's viscosity. Okay. So you retrieve your normal Newtonian fluid, the one on the left. But this is generalizable because now I can change n, right? So what do I get for n, which is less than 1? Yeah, okay, it's a negative tau, good. Any concept for what that would mean? Can you write it another way? I can say. That's the, yeah, dot, the shear. So for n equals 1, we get our Newtonian fluid, right? What do we got for n less than? Let's think about what this relationship is saying again. Okay, so where does this show up? Where did we use this from? Was this, why did we even start talking about this piece of shit? Strain. And we needed this strain because we got incompressible along the way. Before we had this thing Tij, we were calculating what? That's too far back. So at the end of last class, or halfway through last class on Monday, we were doing something. And then we said we need this thing Tij at the end of class. And now we're showing you Tij. Yeah, okay, so we were considering the advection of what? Velocity. So we were thinking about steadiness of velocity, the advection of velocity, and then we had a term there, which was the next term?
Oh, the steady thing, no, could be. Well, we wrote one part as a total derivative.
Yeah, so one part is the total derivative, and that equaled what? Okay, so let's remember what we were doing. We started on Wednesday last week. We said that we wanted to conserve mass. We said, oh, that's super easy. In order to conserve mass, we just have to have Kevin walk in or leave, right? We found that for conserving momentum, it wasn't that easy, right? Because I can generate momentum. How do I generate momentum? Two ways. So that you're thinking about just the term, right? You're like M goes up or V goes up. That's not wrong. That's not how you do it. I have fluid. Make the fluid's momentum change. You could spin it, okay? What would that be? How would I move that fluid? So the first thing you pick it up. Maybe you rotate it like that, right? Okay, so what is that first force? Working against gravity. Now if I dropped it, it would start flowing, right? And then I spin it. That's a surface force. Right? I'm literally forcing the thing around. Right? If this had no viscosity, and I rotate the cup, what happens to the fluid inside? Stay still. How fucking weird is that? I could rotate this cup and nothing would happen to the fluid inside. Okay. So that is a surface force that is distributed by viscosity, a fluid property. And then we said, what the fuck is viscosity? Now we have it. Okay. This is the way that we transfer forces into the fluid. Well, it starts on the surface and it moves in, right? Now, you will have other fluids, so I'm saying this in a way that it's very helpful for you to understand. But once we begin to think about what happens inside the fluids, you'll notice that layers shear against each other. And so you don't have to have a medium going from one to the other in order for them to be creating shear, right? Shear will just happen naturally. Okay, so let's look at this thing again. So this thing here comes from the stress tensor. And the stress tensor was what we used in order to generate momentum. Okay. And we say here, okay, that this relationship, the rate of change of the velocity with respect to the position, if it's associated with an n, then that n can take on various numbers. And all Newtonian fluids have an n of 1. That the relationship between the distribution of velocity in space is linear. But we have non-Newtonian fluids in our lives, unfortunately. And so the question is, for an n that's less than 1, what kind of response do I get? Say that again?
A bigger, also bigger, or greater velocity.
Well, let's make this 1/2. Less than 1. Not less than 0.
Oh.
So the viscosity will go over time, right? Or withdrawn.
Oh, we don't know necessarily anything about this term. This is about how the fluid is distributing it with respect to space, right? Yeah, so this gets smaller. Okay, that would be called a shear thinning fluid. Okay, so for a shear that exists, the thing that I generate, I get a smaller outcome. As opposed to the one that you're quite familiar with, which is n greater than 1. I say quite familiar as though you just learned about it if you. That's your oobleck. So what happens is it essentially acts like a force multiplier. It thickens under shear. And n less than 1 thins under shear. It gets easier to move. So you can think of that a little bit like the difference between kinetic friction and static friction, right? As soon as you start to move the book, it slides easier, right? Similarly, non-Newtonian fluids that are shear thinning, well, that's it. I've said it. I'm not going to draw that analogy too much because I don't want you to actually think that it's a one-to-one analogy. It's not. Okay. Anyone know an example of a shear thinning fluid?
Things under shear, essentially.
You'll probably have to have already worked with it. No, this is not one. Quite. So it's not necessarily about the thickness or the thinness of the oil itself, but the material properties that added therein. So because of this, liquid plastics and polymeric solutions tend to be this way because you have long chain polymers in your fluid, then as they begin to move, they get dragged out and they're not interacting with each other as much. Whereas if you have something like oobleck, now what is oobleck again? It's just water and cornstarch. Water and cornstarch is a suspended solution. And all of a sudden, instead of just having water interacting with water, you have cornstarch molecules trying to interact with other cornstarch molecules. And what happens there is the van der Waals effect, that is to say the intermolecular attraction between those cornstarches becomes stronger. And so they resist the motion. Because remember, all happening on a molecular level. We just observe it at a human scale. Okay.
You think that thing one time that you said towel comes from the stress tension, and we're doing that because we're trying to. Do what? Like, I lost the dirt.
So you lost the plot.
Yeah, I lost the thought.
It's okay. I'm about to give you the plot back. You know, like at the end of the Christopher Nolan film, you're like, fuck, I did understand it the whole time. But you gotta watch it again.
Yeah.
Okay, so we're gonna rewatch this film over and over and over, because I'm about to introduce you to the meat and potatoes, okay? This is the sexiest part of the class, and it is the Navier-Stokes equation. Okay? This is basically the only thing that you need to ever learn in physics. Oh, fluids. Sorry, not physics. Fluids. Shit, don't say that. It's recorded. Okay, yeah, but don't report me. All right. So on the left-hand side, okay, oops, erase it up. I'm gonna write the whole thing out. And then we'll talk about it. All good at this? Exactly the right length. Like the best writer of this equation in like the whole world. Okay, so what the fuck did I do? Anything you recognize? See 2/3 mu. Okay, that's cute. That's the first thing you picked up. I mean, something I did today worked. It's in your book too, so you don't have to write everything down. Just have a look. You only have 6 minutes. Find a term that's your favorite term and tell me what it means. Density times gravity. I love that. What does that mean?
Density is changing. As you like, as your gravity is changing, your density is changing.
Is that a relationship between the gravity and the density?
Oh, no.
Yeah, it's not saying they're in an inverse relationship, right? We don't know what all the terms mean yet, so we don't really know what the relationship is, but it looks similar to something we saw before. So this thing looks like the body forces term. Right? The body forces term was just rho g. And we were like, that's simple, love that. Right? This is the Navier-Stokes equation. And what we're looking at here is a conservation of momentum. On the left-hand side, I have this term is the steady term, right? How is the velocity changing in time? And, of course, how is it changing with space? So is there advection of velocity? Is there generation of velocity? So on the left-hand side, you have the fluid dynamic properties, you know, how the fluid is moving. And then on the right-hand side, you have what? Let me show you what. Here you have delta P, delta X. How is the pressure changing with respect to a certain direction? Okay, so if I have more pressure on one side than the other, then there would be a pressure differential and it would force the fluid to move. That's the first term. This is the pressure term. We pulled it out of this guy and we brought it in the front because everyone loves pressure, it's simple. Okay. This one here, I generate fluid flow from body forces. Something acting on the entire body, whether that is dropping it down a waterfall, whether that's putting it through a magnet, right? I'm creating something that's affecting the whole body. And then this is the one that'll give you fits. Okay? And this is your shears, your stresses. You can't see them, but they're right there. See all the I's and the J's and the J's and the I's? That's your tau, that's your T, that's your S. What's that? Well, each one of these terms we're going to break down, but it's all hidden in there. Okay? And what we're saying here is this is talking about the relative contribution of velocities in directions. Okay? Velocity in direction, velocity in direction. This piece here, this is the velocity in the same direction, so that must of course be velocity in the same direction is compression expansion. So this is the compression expansion term. Here's your shear stresses. Here's your body forces. Here's your pressure differences. And that's how we move.
How is like a first pregnancy kind of?
Don't try to do a one-to-one here. We'll show you that in a little bit. I want you to intellectually understand them first. Okay. Yeah, so you can see that. If you go through the book, you can find 424. That's where we started on, was it Monday? Yeah, starting at the beginning of Monday. We wrote about those body forces. And then we add in the generalized stress tensor. You mix it up, you shake it, you remove it, and you get the Navier-Stokes equation. Okay. Okay. Let's see, what else do I want to say about this? Generally speaking, mu and mu here, this is the viscosity, the bulk viscosity, they're related to one another. Mu naught, mu nu and mu. And we should also note, for example, that have you ever been able to hear the difference between hot and cold running water? You can. And I ask you to try this when you get home, okay? So here's the experiment you want to do when you get home. You have your parent or something, and you pour cold water into a glass. Okay, and then you pour hot water into a glass. Now the other person blindfolded, they can't see. And they have to tell you, now not boiling, but like right before it boils, take it off the kettle, let the bubbles calm down. Pour the hot water, pour the cold water, and listen. I don't know, you tell me. She might be right, but you can hear the difference because the viscosity is temperature bent. And you don't even know this, but your ear is sensitive enough to hear the temperature of water. We forget about how powerful our senses are. That's okay. So I'm running out of time here, but here's how the next couple of weeks are gonna go. Okay, you are gonna see this equation over and over and over. You're gonna see the what's the other one called? The continuity equation. And we're headed towards conservation of energy. Now we'll try and use this, we'll try and understand it in more detail, but essentially we're gonna need to become really familiar with how these types of derivatives impact something, right? So this here, you should understand that's a pressure differential. That is more pressure on one side than the other. As opposed to this, which is advection. And in particular, they look the same, right? They're both spatial derivatives. So sometimes you might say to yourself, what are you talking about? That's just changing in space. But we really want to think about what is the property that's changing in space. Because here, this is a pressure differential, meaning that there's a difference of the pressures. Here, there still is a velocity differential, but what's happening in the fluid is that this is bringing fluid from one place to another, right? Advecting. So the motion itself carries with it momentum. All right, I went a little bit over that, but you get it. And we'll do simplifications too, so that you don't have to always see how horrible that is. Where's my Zoom?
Question?
Yeah.
But when did you